Today, the dot product. Very, very mysterious lesson. I promise you, the mystery of this lesson will get cleared up by the end of the chapter. You've ran into this before in mathematics, where something gets introduced and you're like, what is going on here? And I'll try to give you some taste of what's going on here. And you'll be able to do the homework, but you still might feel a little nervous about what the heck is happening. Give it some time. Trust me, as we go through the days, the clarity of what this all means will come. And it's not clear why we make the choices we do here until later. It's going to happen over the next couple of days in other lessons where you're going to go, oh, that's why we did that like that. Okay? So give it some time. Just worry about what's in this lesson and worry about the context a little later. So the dot product, mysterious name. In our study of vectors, we have considered the operations of adding vectors, subtracting vectors, and multiplying by vectors by scalar. And those operations weren't too bad. Getting to know those wasn't too bad. And this operation, actually doing the operation, won't be too bad. Understanding it will take a couple of days. So we now consider the operation of multiplying two vectors. Good luck understanding what that means to begin with. How could you possibly take two vectors and multiply them? Let me just give a little taste of what that might look like. Imagine I'm in the backyard and I'm pulling on my kid's wagon. There's the wagon. There are two vectors involved. There's which way the wagon's going to go, call that the displacement vector, and then there's this force I'm pulling on here. To find out how much work I'm going to do, how hard I'm going to pull this thing, and how tired I'm going to be when it's over, we've got to multiply these two vectors together somehow. We've got to take that force and multiply it by the displacement. You see, if I use double the force, it's going to be double as much work to me. If I go double the distance, that's going to be double as much work to me. So there's got to be some relationship here between the force and the displacement vectors. That's what we're talking about when we're multiplying vectors. If that sort of makes sense at some level, then we're off to a great start. Because fully understanding that's going to take some time. So we will now consider the operation of multiplying two vectors, and I'll give you a tiny taste of why we'd want to do that or how we would do that. There are actually two different types of vector multiplication. There are actually two different types of vector multiplication in the application of vectors in geometry and physics. And today we'll talk about one called the dot product. Apparently there's another one coming. It'll be called the cross product when we get to it. But for now, we're talking about dot product. And it's actually a fairly simple definition. The dot product is defined as follows. When you want to dot two vectors, and this dot symbol is important here. We use dot for multiplication in vectors when we want to do dot product. And when we want to do dot product, we take the magnitude of the first vector, we multiply it by the magnitude of the second vector, and we multiply it by cos theta, where theta is the angle between u and v when they're tail to tail. All very mysterious why we do those choices. And actually, it all comes from this example I gave right here. You can see if you look at the force and displacement vector, they're sort of pointing in a tail-to-tail direction there, so it makes sense that these things would be tail-to-tail. The angle is going to matter here, so we use the angle in between. Not perfectly explained, but for now, that's the definition. The definition is if you want to do u dot v, you go magnitude u, magnitude v, cos of the angle between. Some notes about the dot product. The dot products of the two vectors is a scalar. You're going to see that in the first example why it's a scalar. The answer when you do dot product will be a number, an amount. So you'll take two vectors, multiply them together, and get a scalar, a number, like 7 or 4.2. So sometimes this is called the scalar product instead of dot product. So that it has another name. Now we define the angle between the two vectors to be the smaller angle formed when two vectors are arranged tail to tail. By smaller, we mean we don't want this. We want this angle in here. We don't want to go all the way around. Therefore, the dot product of perpendicular vectors will be 0. That's so important. There's no way for me to explain right now how important that is. That gets the, I'm going for it. Going red highlighter. Sort of looks orange after I did yellow there. Since if you have 90 degrees between these two vectors, you'll get cos of 90 and you'll get a dot product of 0 because cos of 90 is 0. In my example, why is that? if I pull straight up here, I'm not going to move the wagon in the way I'm talking about, so that I'm not actually pulling in that direction. So that gives you a slight taste of why 90 degrees would give 0. Vectors forming an acute angle have a positive dot product since the cosine of the angle is positive. So if we go cosine of an angle between 0 and 90, we'll get a positive answer. But you can also get a negative dot product if the angle's greater than 90 degrees. Why is that? And just some looking forward here, look at the situation. If my force had been in this direction here, I would have been pulling against the wagon's motion, and I would have been doing what's called negative work, which is I'm taking away energy from the system. So just some physics thrown in there to give some concept of why these things are set up and why they work so well together. Well, anyways, a lot of that is set up for later lessons. In the end, what do you need to understand today? How to find dot product. It says calculate the dot product. You got to know this, that U dot V, to calculate that, we go magnitude U times magnitude of V times cos of the angle between them. But again, that angle has to be tail to tail. In this first warm-up example, they've given it to me tail to tail, so that makes my life very straightforward here. They gave me the magnitude of U, which is a 4. They gave me the magnitude of V, which is a 7. And I got to go cos of 60. I pump that all in my calculator. I get an answer of 14. So you see, this is why it comes out to a scalar number. It gives you a 14. By the way, I can refer this back to my initial wagon example. If I pull with a 4 Newton force and the wagon moves 7 meters and I pull at an angle of 60 degrees, I'll do 14 joules. We don't need to know that word yet, but that's thrown up there for you physics people. I'll do 14 joules of work. So it's very close to a real world example here. And so don't forget, when you're setting these up, highlighter here, the angle used for the dot product is the tail-to-tail angle. And the wagon example is the perfect reason why we want the angle between. Properties of the dot product. Let u, v, and w be 3 vectors, any 3 vectors you want to think about, and let k be a scalar. For a non-zero u and v, so as long as we've got vectors u and v that aren't 0, if u and v are perpendicular, then u dot v will be 0. So important. Doesn't seem like a big deal right now, but it's such a helpful, awesome property. If the cos of the angle is 90, we'll get 0. The reverse is also true. If we find that u dot v is 90, then what we've discovered is that the 2 vectors are perpendicular. Here's another property. If you multiply u by itself, if you do the dot product of u dot u, you get magnitude of u squared. Why does that happen? So if u dotted with u would be magnitude u times magnitude u times cos, what angle between 2 vectors that are the same vector? 0. And cos of 0 is 1, so I get magnitude of u squared. Sort of in a simple algebraic simplification there. If you multiply u with the vector 0, you get 0 because the magnitude of 0 is 0. U dot v is the same as v dot u. I think that's very obvious. Distributive law is in, so you can totally distribute with dot product, and you can totally distribute with scalars as well. We don't prove those things, we just state them. Why are all these things useful? Well, there's 2 ways that they're useful. The first one is to be able to do some vector algebra. All this vector algebra works. Distributive property is in. So if you got 2a vector minus b vector dotted with a plus 3b, a vector plus 3b vector, which really seems weird, but a lot of the algebra we can do, even though we might not totally comprehend what's exactly happening here. To do the distribution, I go 2a dot a plus 6a dot b minus b dotted with a minus 3b dotted with b. That's just pure distribution, pure FOIL I did there, and I just wrote them all out. But I can do a little bit better with some of this stuff using the properties I've just discovered. For instance, a dot a is magnitude a squared, so I can simplify that up a little bit. Not much I can do with a dot b because I don't really know what a and b are, but b dot a is the same as a dot b, so I can reverse that around. That was the commutative law above. And I can do a little bit better with this one. 3 magnitude of b squared. And because I use the commutative law on those middle two to make b dot a and a dot b, I can actually combine these two as well. So just a little taste of some vector algebra there, and that vector algebra isn't going to be that mind-blowing. The symbology is new, but it's sort of the same algebra we've been doing before. You can also use the dot product to find the angle between two vectors just by rearranging the formula. You've got this formula u dot v equals magnitude u, magnitude v, cos theta. If you just divide by u and magnitude v, you get this formula. I don't really memorize this one. You could, and if you like memorizing formulas, this is a good one to memorize. But I just usually rearrange. You know, I memorize this one and just rearrange when I want to find an angle. So good for finding angles. If they give you the dot product, you can find the angles between them. Again, it might not be clear exactly how this stuff's all going to get used, and I'm telling you, it's going to be big, and it's going to be the picture will become clearer. Well, I want to jump ahead to a really tough example, the type of example that it comes up in vectors all the time and seems very mysterious and very scary, but I want to walk through it very carefully and show you some of the power of what you've been given already. The question says if the vectors a plus 3b, whoa, the vector symbols are missing on this version of this. Oops, and that's not going to help at all, is it? Let's actually go to black pencil here. That's vector a plus 3b, and this is 4a minus b. So those are all vectors in there. Oh, and the vectors or symbols are missing here too, so let me just put those on there. So all the vector symbols should be there. And magnitude A is 2 magnitude B. That means the A vector is twice the length of the B vector. I don't know, that doesn't tell me much about their directions, because it says determine the angle between vectors A and B. And a question like this, it totally looks ridiculous. How in the world are you going to find the angle between these vectors with just this information? I just want to talk about one word in this whole thing. It says they're perpendicular. It says this vector and this vector are perpendicular. And that property I mentioned above, which I said was so important, now really comes down. Because if the two vectors are perpendicular, their dot product will be 0. So I start off with this statement. A vector plus 3b vector, because it's perpendicular with this other vector, when I go dot product with 4a vector minus b vector, that must come out to be 0. Seems completely useless. How in the world is that going to help us get the angle? Well, for now, I'm just going to do some algebra and see what comes of all this, okay? So first, some distribution. I'm going to distribute these brackets with FOIL. So I get 4a dotted with a minus a dotted with b plus 12. I could write b dot a here. Maybe I should write b dot a here. But I think that hopefully we're at the stage where you see, okay, ba, we've already seen the commutative property once. That's the same as a dot b. And then I get 3 magnitude b squared. Again, totally mysterious how this answer is possibly going to come out of all this. Because there's not even an angle in all this right now. How are we going to solve for an angle between A and B when I don't even see an angle in all this? But I'm going to carry on and just do what simplification I can, and then I'll work from there. A dot A is magnitude of A squared. We saw that property above. I'm going to add these two things together, collect like terms. That's 11a dot b, and then I get 3 magnitude of b squared. Again, it seems completely ridiculous. Doesn't seem like we're getting anywhere here. Just making a big mess. But this is interesting. The magnitude of a is 2 times the magnitude of b squared. Oh, sorry, the magnitude of 2 times the magnitude of b. I could sub that in. I don't know what that's going to do, but it's going to simplify things a little bit. I can sub it in right here. So instead of magnitude of a squared, I'm going to sub in for magnitude of a and say that magnitude of a is 2 magnitude of b. that all gets squared. I totally get it if your mind's going wild here. You're like, well, what are you doing here? You're just messing around here. And the answer is, yeah, that's exactly what I'm doing. I'm just sort of messing around with this stuff and using the vector algebra that I've been given. What happens here? I get 4 times 4 magnitude of b squared. I just square both things in the brackets. Oh, and that becomes 16 magnitude of b squared. And all of that seems like a big waste of time, except look, that little bit of work there really helped because I've got 16 magnitude b squared and subtract 3 magnitude b squared. I can put those together. Oops. Now, the big moment. And maybe this moment should have happened earlier. Maybe I was dramatizing this a little bit. As soon as a dot b was in there, the angle was in there. You're like thinking, well, how can we possibly get the angle out of there? As soon as there was dot product involved, like right from the beginning, right here, let me highlight it. This moment right there, when I wrote dot product there, the angle was in the algebra. I just hadn't wrote it yet. Because a dot b is magnitude A, magnitude B, times cos of the angle between them. Big moment. It gives you a chance at this because maybe now we can find theta by isolating it. How are we going to isolate it? Well, first, let's just move that other term over. And that doesn't look great, but I'm going to use this again. This magnitude of A is bothering me because things would be good if I didn't have that in there. So I'm going to replace that again, like I did before, with 2 magnitude B. And so when I multiply that whole big mess, what I get is 22 magnitude of B squared cos theta equals negative 13 magnitude of B squared. And hopefully I've held your brain just long enough to get to this step, because look what happens here. When I solve for cos theta, I get negative 13 magnitude of B squared over 22 magnitude of B squared. And those magnitude of B's go. What color am I going to use to cancel out? A nice green. Gone. And what I get is cos theta equals negative 13 over 22. And you think you're home free, except you're not. You need a little bit of trig here to be able to handle this situation. A negative cos, what could be going on here? It's got to be CAST. It must be in this quadrant here to be negative. Adjacent 13. Hypotenuse 22. So to get that related angle in there, which I'll call R, I got to go, R is the cos inverse of 13 over 22. When I do cos inverse of 13 over 22, I get 54 degrees as the related acute angle, and so therefore theta is 180 minus the 54, and I get 126 degrees. I don't want you to freak out about the trig in the middle of all this. There is some trig in this chapter. The trig just popped its head in the middle of that question. That question was really about vector algebra, not about the trig at the end. But that's not the craziest trig there at the end. That's just a little bit of cast rule, a little bit of inverse cos there, so nothing too wild there. Okay, that's example supposed to be a taste of what's coming, of the power of this vector algebra to be able to find angles, find unknowns in vectors in seeming situations that seem like it's impossible to be able to discover what they're asking for. Okay, this is a completely new concept. I don't want you to freak out about it. I want you to try the homework and see what the homework's asking of you in all of these things. Get to know dot product a little bit, and in the future days, we'll see more and more about dot product and its power. But this lesson's designed to see the very basics of dot product all the way up to some of the awesome power of dot product. Okay, folks, have a great day.